In a first-year chemistry course, we talk about single replacement and double replacement, combustion, synthesis, and decomposition type reactions. In this class, we're going to divide things slightly differently. We've already talked about two types of double replacement, precipitation and acid-base reactions. And then we can take a look at all of these different reactions as redox reactions. So here are a few common examples. In the synthesis reaction, the lead is being oxidized, the nitrogen is being reduced. Sodium oxidized, chlorine reduced. In a decomposition reaction, we have mercury being reduced and oxygen being oxidized. In propane, the carbon is being oxidized, the oxygen is being reduced. And in single replacement reactions, magnesium is being oxidized and copper ions are being reduced. Or zinc is being oxidized and hydrogen ions are being reduced. So all of these different types of reactions are redox reactions. So let's review what redox is. Redox reactions are the transfer of electrons in a chemical reaction. And so there are two half reactions associated with it. Oxidation. Oxidation is loss of electrons, and reduction, which is gain of electrons. How do you remember which is which? Well, there's a bunch of different ways, but I like to use, see if I can get this to right, oil rig. Oxidation is loss, reduction is gain of electrons. So oil rig reminds us that oxidation is losing our electrons, reduction is gaining our electrons. And so I added a couple more really important redox reactions: photosynthesis and respiration, the way batteries work. All of these are redox reactions. So as we talk about redox reactions, one of the things we're going to use is something called an oxidation number. Oxidation numbers help us to keep track of how the electrons are transferred. A higher oxidation number, more oxidized. Lower oxidation number, more reduced. So if we go back and look at those original reactions on the previous slide, we can see which atoms get oxidized and reduced, and we're going to take a look at that in a few minutes. One note, ion charges are real, they're measurable. We can measure conductivity and see that a calcium ion has a +2 charge and a sodium ion has a +1 charge. Oxidation numbers in covalent molecules, or in the middle of an ion, those are things that we made up to help us figure out whether things are oxidized or reduced. So here is an example. This vanadium ion with a +3 charge is a V3+ ion, and it's green. This vanadium ion with a +2 charge, which is purple, really has a +2 charge. This vanadate ion has a vanadium 5. Well, there's not really a vanadium 5. It has an oxidation number of +5 in that ion. So these have oxidation numbers that exist, but there is no vanadium +4 or vanadium +5 ions by themselves. Hopefully that wasn't too confusing. By following this set of rules, we'll be able to assign oxidation numbers to any element in any substance. So first, neutral species, meaning atom or molecule, if you add up all the oxidation numbers, the total should be 0. In an ion, if you add up all the oxidation numbers, you get the charge of an ion. So sulfate should have oxidation numbers that add up to -2. Ammonium should have oxidation numbers that add up to +1. First rule, if it is a pure element, it has an oxidation number of 0. So chlorine gas, Cl2, oxidation number of 0. Fe, iron, oxidation number of 0. Next set of rules, group 1A metals, always +1. Group 2A metals, always +2. Those are easy to remember because those are the charges on the ions. Lithium, potassium, sodium, +1. Calcium, magnesium, barium, beryllium, +2. Fluorine is going to be -1 whenever it's part of a compound. Next set of rules. A monoatomic ion, the oxidation number is the ion charge. So, for example, Fe3+ has an oxidation number of +3, where Fe2+ has an oxidation number of +2. In a polyatomic ion, we're going to use the rules above and below, but then, again, as I mentioned before, the oxidation numbers add up to the ion charge. Almost all the time, hydrogen will have a +1 oxidation number. The only examples that are not the case for hydrogen are when they are metal hydrides, so sodium hydride, calcium hydride, or when it's pure hydrogen H2 gas. Almost all the time, oxygen will be -2. There are a couple of weird examples like hydrogen peroxide with a -1, or even weirder ones called superoxides where it's -1/2, but don't start using those very frequently. So for example, in lead-4 oxide, this oxide has a -2 oxidation number. And because it's lead-4, lead has a +4 oxidation number. One of the things you might have noticed is this is a fraction, and that's possible. Remember, these are not real charges. Real charges are based on sums of protons and electrons. These are things that we create to try to keep track of redox. And then a lot of the others, we're going to be using arithmetic and the rules above. So let me show you how that works. The first 5 substances all have iodine in them, and they're going to have different oxidation numbers. So I'm going to start with the easiest ones. So I2, iodine being a pure substance, has an oxidation number of 0. Sodium iodide is also pretty simple. Sodium is a +1 because it's in group 1. Iodide ion is a -1 because being in group 17, it's a -1 ion. The other ionic compound that is pretty simple, copper is a +2, and iodine, let me erase that, is a -1. Copper 2 iodide. The others will take a little more work to figure out. So for potassium iodite, we have potassium is a +1, and we know oxide is a -2. So I can actually use a little bit of algebra to calculate the oxidation number of the iodine. I have a +1 and the iodine, and 2 negative 2's, and because it's a neutral substance, it has to total up to be 0. So +1 plus iodine minus 4, iodine has to be a +3 oxidation number. I3 minus is a slightly weird one. There are 3 iodine atoms, and there's a total charge of -1, meaning the oxidation number is -1/3. As I said, kind of weird. So let's take a look at the carbons. Here I have 4 different submolecules. Each of them contain carbon, and let's take a look at their oxidation numbers. First thing I'm going to do is assign the oxygen and the hydrogen. So oxygen is -2, hydrogen is +1, oxygen is -2, hydrogen is +1. Then I'm going to do a little bit of arithmetic. And I typically do this arithmetic in my head. I am just showing it so that you can see what I'm thinking. The carbon plus 2 negative 2's has to total 0. So in this case, carbon is a +4. In the second case, there are 2 carbons, and add them to the 6 hydrogens, and they have to total 0. So now my carbon is more reduced. It has a -3 oxidation number. This carbon has a +2 oxidation number, +2 -2. And this last one, the carbon has a -2 oxidation number. So go to the next slide and give them a try. See which ones you can figure out. Pause the video, and when you're done, take a look at the answers. Let's take a look at the answers. The first thing I did was, in black, mark all the ones that I could do by just a visual inspection. Pure elements like oxygen, chlorine, manganese, and sulfur have an oxidation number of 0. Then I went through and did my hydrogens as +1s and my oxygens as -2s. And I gave chloride a -1 because that's its charge in ionic compounds. The next step is to do the other ones that were fairly simple. So in HCl, a binary compound, if H is a +1, Cl has to be -1. In Mn2O3, if oxygen is a -2, Mn has to be a +3. So if you take a look at the ones that I wrote in blue, that's the ones I figured out next. The next set were the ones in red. So for HClO, I knew a +1 and a -2, Cl had to be a +1. For ClO2-, I knew oxygen's a -2, and there are 2 of them. The total has to be -1, so the chlorine has to have an oxidation number of +3. The one that confuses most people is number 15. How do you know that Cl is a -1? Well, it's the most common oxidation number when it's written second. It's not really an anion, but so let's say chlorine is a -1, sorry. That makes sulfur a +1. This one looks complicated, but it's really not. NH2OH is written this way because it's a nitrogen attached to a hydrogen, a second hydrogen, and an OH. But we really think of the hydrogens as +1s, the oxygen as a -2, and it's pretty easy to calculate the nitrogen. So in terms of calculating oxidation numbers, that's all there is to it. We can use oxidation numbers to decide what's being oxidized and what's being reduced. So if we take a look at the first example, copper ions go from a +2 down to a 0, copper metal. A reduction in oxidation number means electrons have to be added. That's reduction. Magnesium increases oxidation number. It gets more oxidized. And I can do the same thing looking at my silver and my calcium. So again, pause the video and work through the rest of the problems on this page. Take a look at the answers when you're done. As we take a look at these answers, there's a couple of things I want you to notice. First, there are all sorts of elements that don't get oxidized or reduced in a balanced equation. Second, there will always be one element being reduced and one element being oxidized. We're not going to have two things being reduced, two things being oxidized. It's going to be one, and then a lot of other things that are just necessary and come along for the ride. And as oxidation number goes down, 0 to -1, 0 to -2, +7 to +2, that tells us that that element is being reduced. As the oxidation number increases, +3 to +4, or -2 to 0, that's a sign of oxidation. And the last thing in this section is balancing half reactions. So to balance a half reaction, like we do with any other type of balanced equation, we have to obey the law of conservation of matter. So atoms and charges have to be equal. And a lot of times these are going to be net ionic equations. So first we want to write the half reactions. So in this example, it would be copper going to copper 2+, and silver ion going to silver. And we need to show how many electrons are needed. So the first one is an oxidation, 2 electrons. The second one is a reduction. We add in 1 electron. Step 3, balance the electrons. So to do that, I'm going to multiply everything in the second half reaction by 2. Then the electrons get crossed off because they're the same on both sides. And I have 2 silver ions and a copper atom, forming a copper 2 ion and 2 silver atoms. The key here is that the number of electrons lost and the number of electrons gained have to be the same. Let's take a look at the second example. One half reaction involves the iron. I go from Fe2+ to Fe3+ and 1 electron. The second one is a little tougher. I have Cr2O7 with a 2- charge and H+, forming H2O and Cr3 plus. I need to balance my atoms first. 2 chromiums, so I need 2 chromiums. 7 oxygens on the left, so I need 7 oxygens on the right, meaning I need 14 H pluses. Now I have to figure out how many electrons I need. And this is where oxidation numbers come in handy. My chromium is a +6 and a +3. So my oxidation number changes by 3, and there are 2 of them, so that's a total of 6 electrons. Let me say that again. Chromium goes from a +6 to a +3. That's a change in oxidation number of 3. We know it's reduction, so we're gaining electrons. And there are 2 chromium atoms, so 2 times 3 is 6 electrons. Now I need to balance, so I need 6 of the iron half reaction, and then I add them all up, crossing the electrons off. Cr2O72 minus plus 14H plus 6 Fe2 plus makes 6 Fe3 plus and 7 H2O and 2 Cr3 plus. If I go back and double check, I have 2 chromium on the left, 2 chromium on the right, 7 oxygens on each side, 14 hydrogens, 6 irons. My total charge on the left is -2 plus 14, which is plus 12. Plus 12 is 24. 18 and 6 is 24. So that is how we balance redox reactions. Hopefully, this gave you some information about redox, and if you have any questions, as always, let me know.